Picture this. You're standing on a planet that looks absolutely nothing like the Earth we know today. The sky burns orange, toxic gases choke the atmosphere, and the ground beneath your feet is a molten hellscape where nothing can survive. This isn't some distant alien world from science fiction. This is our Earth during one of the most catastrophic periods in its history. What if I told you that our beautiful, life-filled planet has been brought to the brink of total annihilation not once, not twice, but 5 separate times? These weren't just bad days for the dinosaurs. These were apocalyptic events so devastating that they wiped out up to 95% of all life on Earth. Yet somehow, against all odds, life found a way to bounce back each time, setting the stage for the incredible diversity we see today. Today, we're going on an extraordinary journey through deep time to witness the 5 most catastrophic mass extinctions in Earth's history. We'll explore how our planet looked during these dark chapters, what caused such widespread destruction, and most importantly, how life managed to survive and evolve in ways that eventually led to us sitting here right now. But here's what makes this story even more compelling. Scientists are now debating whether we're currently living through a 6th mass extinction, one caused not by asteroids or volcanic eruptions, but by human activity. By understanding what happened during these ancient catastrophes, we might just gain crucial insights into our planet's future. So buckle up, because we're about to travel back hundreds of millions of years to witness some of the most dramatic events in Earth's history. And trust me, what you're about to discover will completely change how you see our planet and our place on it. Let's start our journey roughly 4.5 billion years ago, when Earth first formed. Back then, our planet was completely unrecognizable. Imagine a world shrouded in a thick, suffocating atmosphere of methane, ammonia, and other toxic gases. The surface was a nightmare of molten rock, with temperatures hot enough to melt lead. There were no oceans, no continents as we know them, and certainly no life. But Earth began to cool, and something magical happened. Water vapor in the atmosphere condensed and fell as rain for thousands of years, filling the low-lying areas and creating the first oceans. This was the birth of what scientists call the hydrosphere, and it set the stage for one of the most important developments in cosmic history: the emergence of life. Around 3.5 billion years ago, the first simple life forms appeared in these ancient seas. These weren't the complex creatures we're familiar with today. They were microscopic, single-celled organisms that could barely be seen even under a powerful microscope. But these tiny pioneers had something revolutionary. They could reproduce themselves and maintain their internal chemistry despite the harsh conditions around them. For billions of years, these simple cells dominated Earth's oceans. They were incredibly small, measuring just fractions of a millimeter, but they were busy transforming our planet in ways that would make all future life possible. Through photosynthesis, they began converting carbon dioxide in the atmosphere into oxygen, slowly but steadily changing the very air that surrounded our world. As time passed, something extraordinary occurred. These individual cells began working together, forming the first multicellular organisms. This was a game-changing development, because it allowed life to become more complex and specialized. Different cells could take on different roles, just like how different organs in our bodies have specific functions. Then, around 540 million years ago, something happened that paleontologists call the Cambrian explosion. This wasn't literally an explosion, but rather an incredible burst of evolutionary creativity. In a relatively short period of geological time, life diversified into an amazing array of forms. The oceans became filled with creatures that looked like alien beings from another world. Bizarre arthropods with multiple eyes, soft-bodied animals that resembled living flowers, and predators with grasping appendages that could snatch prey from the water. During this period, the first animals with hard shells and exoskeletons appeared, which is why we have such good fossil records from this time. These protective coverings not only helped creatures survive, but they also preserved beautifully in the rock record, giving us a window into this ancient world. The seas teemed with trilobites, those iconic three-lobed creatures that would become some of the most successful animals in Earth's history. Some were tiny, smaller than a coin, while others grew to the size of dinner plates. They had compound eyes that could detect the slightest movement in the water, and many had elaborate spines and decorations that made them look like living jewelry. Alongside the trilobites lived the brachiopods, creatures that looked somewhat like clams but were actually quite different. They had two shells, but unlike modern clams, these shells were positioned top and bottom rather than left and right. Inside their shells, they had intricate feeding structures that could filter tiny particles of food from the water. The ocean floor was carpeted with strange gardens of sponges and early corals, creating the first complex ecosystems our planet had ever seen. Predators stalked through these underwater forests, including the fearsome Orthoceras, straight-shelled relatives of modern squid that could grow longer than school buses. But even as life was flourishing in the oceans, the land remained completely barren. The atmosphere still didn't have enough oxygen to support complex life on dry ground, and the landscape was nothing but bare rock and sand, battered by intense solar radiation and fierce storms. This was the setting for our first mass extinction, and it came from the most unlikely source, outer space. Picture this scene. It's a normal day in the ancient ocean, roughly 445 million years ago. Trilobites are scuttling across the seafloor. Brachiopods are filtering food from the water, and coral reefs are bustling with activity. The sun is shining down through the clear water, supporting countless photosynthetic organisms. Then, in an instant, everything changes. Thousands of light years away, a massive star reaches the end of its life and explodes in what astronomers call a supernova. But this isn't just any supernova. This stellar death produces one of the most destructive phenomena in the universe, a gamma-ray burst. Imagine the energy of 1,000 suns concentrated into a beam of radiation traveling at the speed of light. This cosmic death ray pierces through space for thousands of years before finally reaching Earth. When it hits our planet's atmosphere, it triggers a chain reaction that would make a nuclear bomb look like a firecracker. The gamma rays slam into the molecules in our atmosphere, tearing them apart and recombining them into new, deadly compounds. Within seconds, about a third of Earth's protective ozone layer is destroyed. This invisible shield had been protecting life from the sun's harmful ultraviolet radiation, and now it was gone. Suddenly, the sun became a weapon. Ultraviolet radiation, now 50 times more intense than normal, began streaming down to Earth's surface. The ocean, which had been a safe haven for life, became a death trap. The intense radiation killed the tiny floating organisms that formed the base of the food web, causing a cascade of starvation that rippled through every level of the ecosystem. But the cosmic catastrophe wasn't finished. The gamma rays had also transformed nitrogen and oxygen in the atmosphere into nitrogen dioxide, creating a brownish haze that blocked sunlight but trapped heat. This led to rapid climate change, with the planet swinging between devastating heat and bone-chilling cold. As temperatures plummeted, massive glaciers began forming, locking up huge amounts of water and causing sea levels to drop dramatically. Shallow coastal areas where most marine life lived became dry land. Creatures that had never known anything but water suddenly found themselves stranded and dying. The cold persisted for hundreds of thousands of years. Ocean temperatures dropped so low that many species simply couldn't survive. Coral reefs, which had taken millions of years to build, were destroyed in mere decades. The trilobites, those incredibly successful arthropods, saw their numbers crash as their food sources disappeared. Yet even in this frozen wasteland, some life persevered. Small primitive fish called astropis managed to survive by being incredibly adaptable. Unlike the specialized predators that could only eat specific prey, these little fish would eat almost anything they could find. They followed the retreating shorelines, adapting to colder temperatures and lower oxygen levels. These humble survivors don't look like much in the fossil record, but they represent one of the most important lineages in Earth's history. They possessed the first primitive backbones, making them the ancestors of every vertebrate animal alive today, including birds, mammals, reptiles, and ultimately us. The first mass extinction, known as the Ordovician-Silurian extinction, eliminated roughly 70% of all species on Earth. It was a devastating blow to the planet's biodiversity, but it also cleared the way for new evolutionary experiments. The survivors found themselves in a world with fewer competitors and more opportunities. As the Ice Age finally ended and temperatures began to rise, life started its remarkable recovery. The few species that had made it through the cosmic catastrophe began to diversify and adapt to fill the empty ecological niches left by the extinct creatures. Fish evolved new feeding strategies, developing the first primitive jaws that would later become one of the most important innovations in vertebrate evolution. Some of the survivors took an even bolder step. Giant sea scorpions called eurypterids, some as large as modern crocodiles, developed primitive lungs that allowed them to venture onto land for short periods. These fearsome predators were among the first complex animals to explore the terrestrial world, paving the way for the eventual colonization of land by life. The recovery from this first mass extinction set the stage for the next great chapter in Earth's history. As we'll see, our planet was about to enter another period of incredible diversity and evolutionary innovation, only to face an even more devastating catastrophe that would test life's resilience once again. But that's a story for our next chapter, where we'll explore how Earth transformed from this ice-bound world into a lush, tropical paradise teeming with bizarre creatures, only to face destruction from forces brewing deep within the planet itself. The Earth that emerged from this first great dying was like a blank canvas waiting for evolution's next masterpiece. As the glaciers retreated and temperatures stabilized, our planet began transforming into something truly spectacular. The Devonian period, often called the Age of Fishes, was about to begin, and with it came innovations that would reshape life forever. Picture the world roughly 400 million years ago. The supercontinent that geologists call Gondwana dominated the southern hemisphere, while smaller land masses dotted the northern regions. The climate was warm and humid, creating perfect conditions for life to flourish. Ocean temperatures hovered around a comfortable 77 degrees Fahrenheit. And for the first time in Earth's history, something remarkable was happening on land. The barren landscapes that had persisted for billions of years were finally turning green. Primitive plants, descendants of the green algae that had survived in shallow coastal waters, made their first tentative steps onto dry ground. These weren't the towering trees we know today, but rather humble mosses and simple ferns that hugged the ground like a living carpet. But it was in the oceans where the real action was taking place. The fish that had survived the Ordovician extinction were undergoing an evolutionary explosion that would make the Cambrian period look tame by comparison. New species were appearing at an unprecedented rate, each one more bizarre and specialized than the last. The most dominant creatures of this underwater realm were the placoderms, armored fish that looked like swimming tanks. These revolutionary predators had something that would change the course of evolution forever: jaws. For the first time in Earth's history, vertebrates could actively hunt, bite, and tear their prey apart. Some of these armored giants grew to enormous sizes, with skulls alone measuring over 3 feet long. The largest and most terrifying of these was Dunkleosteus, a monster that ruled the ancient seas like a prehistoric great white shark. But instead of teeth, this 30-foot predator had razor-sharp bony plates that could slice through almost anything. Its bite force was estimated at over 11,000 pounds per square inch, making it one of the most powerful predators that ever lived. Swimming alongside these armored giants were the first sharks, sleek and efficient killers that had perfected a body plan so successful that it remains virtually unchanged today. But these weren't the only fish exploring new evolutionary possibilities. Some species were developing something that would prove even more revolutionary than jaws: lungs. These lung-equipped fish weren't planning to leave the water permanently. Instead, they were adapting to environments where water levels fluctuated dramatically. During dry seasons, when ponds and streams began to evaporate, these remarkable creatures could gulp air and survive until the rains returned. Meanwhile, on land, those pioneering plants were busy transforming the atmosphere. Through photosynthesis, they were pumping unprecedented amounts of oxygen into the air, creating an atmosphere richer in this life-giving gas than Earth had ever experienced. This oxygen revolution was setting the stage for even bigger changes to come. Some of those lung-equipped fish began spending more and more time in the shallow waters near shore, where dense vegetation created a maze of roots and fallen logs. In this cramped environment, their fins began changing shape, becoming more like primitive legs. These creatures weren't trying to walk on land. They were simply adapting to push through the underwater jungle more effectively. But evolution rarely moves in straight lines, and these adaptations were preparing life for one of the most important transitions in Earth's history. The first tentative steps onto land were still millions of years away, but the foundations were being laid during this remarkable period of innovation and growth. The diversity of life during the Devonian was truly staggering. Coral reefs stretched for thousands of miles, creating underwater cities that supported countless species. Trilobites, those survivors from earlier extinctions, had bounced back with a vengeance, evolving into new forms with elaborate spines and decorations. Some developed enormous eyes that could detect the faintest traces of light in the deep ocean. Sea lilies, despite their name, actually animals related to starfish, created underwater forests that swayed in the ocean currents like alien trees. Brachiopods carpeted the seafloor in such numbers that their shells would eventually form entire limestone mountains. And swimming through this underwater paradise were nautiloids, relatives of modern octopus and squid, some with shells coiled into perfect spirals and others with straight shells longer than telephone poles. But deep beneath the ocean floor, forces were stirring that would bring this golden age to a catastrophic end. The Earth's interior, a churning mass of molten rock and superheated gases, was building pressure like a cosmic pressure cooker. What was about to happen would make the gamma ray burst that ended the Ordovician look like a gentle summer shower. The second great mass extinction was brewing in the depths of our planet, and when it finally erupted, it would unleash forces so destructive that they would fundamentally alter the chemistry of the entire planet. Massive volcanic eruptions would poison the atmosphere, boil the oceans, and plunge the world into chaos that would last for millions of years. Deep beneath what we now call Siberia, an enormous plume of superheated rock was rising from the Earth's core. This wasn't just any volcanic eruption waiting to happen. This was a geological monster that would make modern volcanoes look like tiny firecrackers. The magma chamber that was forming contained enough molten rock to bury an entire continent under a mile of lava. As this underground inferno grew larger and more unstable, life on the surface continued its peaceful existence, completely unaware of the doom that was approaching from below. The fish swam in their coral gardens. The early plants spread across the land, and evolution continued its patient work of creating new forms and possibilities. But the planet was a ticking time bomb, and the clock was running out. The pressure beneath Siberia finally reached its breaking point around 370 million years ago. The Earth's crust cracked like an eggshell, and hell literally broke loose. Imagine volcanic eruptions so massive that they could be seen from space if anyone had been there to witness them. Lava fountains shot hundreds of feet into the air, and rivers of molten rock began flowing across the landscape at temperatures hot enough to vaporize anything in their path. But the lava itself was just the beginning of this planetary catastrophe. The real killer was what came with it: toxic gases that poured into the atmosphere in quantities that beggar the imagination. Carbon dioxide, sulfur compounds, and other poisonous vapors began changing the very chemistry of Earth's air and water. The ocean, which had been a crystal clear blue paradise, began turning into a toxic soup. When the superheated lava met seawater, it triggered massive underwater explosions that sent clouds of steam and poisonous gases billowing into the atmosphere. The water temperature began rising dramatically, climbing from a comfortable 77 degrees to a scalding 90 degrees Fahrenheit. Marine life, which had evolved in cool, oxygen-rich waters, suddenly found itself in a hostile environment that resembled a giant hot tub filled with poison. The coral reefs, those magnificent underwater cities that had taken millions of years to build, began dying en masse. Fish floated to the surface in enormous numbers, victims of the toxic cocktail that their home had become. On land, the situation was equally dire. The massive volcanic eruptions had thrown so much ash and gas into the atmosphere that the sun's light was blocked for months at a time. Plants, which depended on sunlight for photosynthesis, began dying in massive numbers. As the plant life collapsed, so did the few animals that had begun to colonize the terrestrial world. The poisonous gases didn't just kill directly, they also triggered a cascade of climate changes that made life nearly impossible. The carbon dioxide released by the volcanoes created a runaway greenhouse effect, trapping heat in the atmosphere and sending temperatures soaring even higher. At the same time, other volcanic gases created acid rain that burned through whatever vegetation managed to survive the initial onslaught. But perhaps the most insidious effect was what happened to the ocean's oxygen. As temperatures rose and toxic chemicals poured into the water, the tiny organisms that produced most of the ocean's oxygen began dying off. Without these microscopic powerhouses, oxygen levels in the water plummeted, creating vast dead zones where nothing could survive. The few creatures that managed to avoid immediate death found themselves in a world where the rules of survival had completely changed. The armored placoderms, those apex predators that had ruled the seas for millions of years, discovered that their size and power were now liabilities. In the oxygen-depleted waters, large animals simply couldn't get enough of the gas they needed to fuel their massive bodies. Meanwhile, smaller, more adaptable creatures had a better chance of survival. Those primitive fish with lungs could supplement their oxygen intake by breathing air, giving them a crucial advantage in the suffocating seas. But even they faced enormous challenges as their food sources disappeared and their habitats transformed into alien landscapes. The Devonian extinction didn't happen overnight. It was a slow-motion catastrophe that unfolded over millions of years, with multiple pulses of destruction that eliminated wave after wave of species. Each time life seemed to be recovering, another volcanic eruption would restart the cycle of death and destruction. By the time the worst of the volcanic activity finally subsided, the damage was almost incomprehensible. Roughly 75% of all species on Earth had vanished forever. The magnificent coral reefs were reduced to scattered remnants. The diverse communities of brachiopods and trilobites were decimated, and the early experiments in terrestrial life were set back by millions of years. Yet once again, life proved its remarkable resilience. Among the survivors were creatures that would go on to achieve something that had never happened before in Earth's history. They would finally, successfully colonize the land. The extinction had cleared away many competitors and opened up new ecological opportunities for the species that remained. Those lung-equipped fish, having survived the oxygen crisis in the water, began making longer and longer excursions into the shallow areas where land met sea. Their fins, already modified for navigating through dense vegetation, gradually became more leg-like. Over millions of years, these aquatic pioneers would evolve into the first true amphibians, animals that could live both in water and on land. The recovery from the Devonian extinction set the stage for one of the most important chapters in the story of life, the conquest of the continents. For the first time, vertebrate animals would walk on dry ground, breathe air, and explore environments that had been completely lifeless since the planet formed. But as we'll discover, this was just the beginning of an even more dramatic story. The Earth was about to enter a period of incredible diversity and evolutionary experimentation that would culminate in the rise of the first great land animals. Unfortunately, it would also set the stage for the most devastating mass extinction in our planet's history, an event so catastrophic that it would bring complex life to the very brink of total annihilation. The story of how life survived that ultimate test and how it emerged to create the world we know today is perhaps the most remarkable tale of resilience and adaptation ever told. As the Earth slowly healed from this second great catastrophe, something extraordinary began to unfold. The survivors didn't just recover. They embarked on one of the most ambitious evolutionary adventures in our planet's history. For the first time since life began, complex creatures were about to leave the safety of the oceans and make the radical leap onto dry land. The world that emerged from the Devonian extinction was like a laboratory for evolutionary innovation. With so many ecological niches suddenly empty, the surviving species found themselves with unprecedented opportunities to explore new ways of living. And explore they did, in ways that would fundamentally reshape the very definition of what it meant to be alive on Earth. Picture the landscape roughly 350 million years ago, as we enter what geologists call the carboniferous period. The climate was warm and humid, creating conditions that were absolutely perfect for plant growth. The simple mosses and ferns that had survived the extinction began evolving into something the world had never seen before: forests. But these weren't just any forests. These were alien wonderlands that would look completely foreign to our modern eyes. Towering tree ferns reached heights of over 100 feet, their fronds creating a canopy that filtered the sunlight into an ethereal green glow. Giant horsetails, relatives of tiny plants you might find in a modern garden, grew as tall as telephone poles and formed dense thickets along ancient riverbeds. The most spectacular of these ancient giants were the scale trees, massive plants that could grow over 150 feet tall and 6 feet across. Their bark was covered in a diamond pattern of scars where leaves had once attached, giving them an almost reptilian appearance. When these giants finally died and fell, they would eventually become the coal deposits that would fuel the Industrial Revolution hundreds of millions of years later. Living in this prehistoric jungle were creatures that seemed to come straight out of a science fiction movie. Dragonflies with wingspans of over 2 feet buzzed through the humid air, their massive eyes scanning for prey. These weren't just oversized versions of modern insects. They were perfectly adapted predators that could snatch smaller flying creatures right out of the air with incredible precision. On the forest floor, millipedes the size of cars crawled through the decaying vegetation, some reaching lengths of over 6 feet. Their bodies were armored with tough plates that protected them from the various predators that stalked through the underbrush. But perhaps most remarkable of all were the first creatures that had truly mastered life on land, the early amphibians. These pioneering vertebrates had evolved from those lung-equipped fish that survived the Devonian extinction, and they represented one of the most significant evolutionary breakthroughs in Earth's history. Creatures like Ichthyostega looked like a bizarre cross between a fish and a salamander, with powerful limbs that could support their weight on land, but a body that was still clearly adapted for life in the water. These early landwalkers weren't graceful movers. They probably spent most of their time in shallow water, using their limbs to push through dense vegetation or to haul themselves onto muddy banks to escape aquatic predators. But they had achieved something that no vertebrate had ever done before. They could breathe air and move around on solid ground. As millions of years passed, these amphibious pioneers gave rise to even more specialized land animals. Some evolved into purely terrestrial creatures that could venture far from water sources. Others developed new reproductive strategies, laying eggs with tough shells that could survive on dry land instead of requiring the aquatic environment that their ancestors had depended on. The innovation that would prove most revolutionary was the evolution of the amniotic egg. This might not sound particularly exciting, but it was actually one of the most important developments in the history of life. These special eggs contained everything a developing embryo needed to survive on land: a food source, waste storage, and most importantly, a protective membrane that prevented the embryo from drying out. This breakthrough led to the rise of the first true reptiles, creatures that were completely independent of water for reproduction. They could colonize environments that were completely inaccessible to their amphibian cousins, spreading across the continents and diversifying into an incredible array of forms. Some of these early reptiles remained small and agile, darting through the undergrowth in search of insects and other small prey. Others grew to impressive sizes, becoming the apex predators of their terrestrial ecosystems. And a few developed one of the most important innovations in the history of animal life: the ability to regulate their own body temperature. These early experiments in warm-bloodedness allowed certain reptiles to remain active even when environmental temperatures dropped, giving them a huge advantage over their cold-blooded relatives. Some developed elaborate sails on their backs that could absorb heat from the sun or dissipate excess warmth when necessary. Others evolved the first primitive fur-like coverings that helped insulate their bodies against temperature fluctuations. Meanwhile, in the oceans, life was also undergoing remarkable changes. New types of sharks evolved that were even more efficient predators than their Devonian ancestors. Massive marine reptiles began appearing, some growing to lengths that rivaled modern whales. And in the shallow seas, entirely new ecosystems developed around communities of creatures that looked like underwater flower gardens, but were actually colonies of tiny animals. The diversity of life during this period was truly staggering. Forests covered vast areas of the continents, creating complex three-dimensional habitats that supported countless species of plants, insects, amphibians, and reptiles. The oceans teemed with fish, marine reptiles, and invertebrates that had evolved amazing adaptations for life in their aquatic realm. But perhaps most remarkably, this was also the period when life first began to significantly modify the environment on a global scale. Those massive forests were pulling enormous amounts of carbon dioxide out of the atmosphere and converting it into plant matter that would eventually become buried and preserved as coal deposits. This biological carbon sequestration was actually cooling the planet, setting up conditions that would lead to one of the most dramatic climate changes in Earth's history. As carbon dioxide levels dropped and temperatures began to fall, ice caps started forming at the poles for the first time in hundreds of millions of years. Sea levels dropped dramatically as water became locked up in massive glaciers, exposing vast areas of the continental shelves and creating new land bridges between continents. These climate changes created both opportunities and challenges for the life forms that have been flourishing in the warm, humid conditions of the earlier carboniferous. Some species adapted to the cooler, drier conditions, while others retreated to refuges near the equator, where tropical conditions persisted. But even as life was adapting to these gradual climate changes, forces were building deep within the Earth that would soon unleash the most devastating catastrophe in our planet's history. The supercontinent Pangaea was forming as the various land masses slowly collided and merged together. This massive geological reorganization was creating enormous stresses in the Earth's crust, and pressure was building in the mantle that would eventually find release in the most catastrophic volcanic eruption ever recorded. The stage was being set for what scientists call the Great Dying, an extinction event so severe that it would eliminate over 90% of all life on Earth. This wasn't going to be a gradual decline or a regional catastrophe. This would be a global apocalypse that would test life's ability to survive under the most extreme conditions imaginable. The Permian period had given rise to some of the most spectacular creatures ever to walk the earth. Massive reptiles with bizarre sail-like structures on their backs roamed the continents. Early relatives of mammals developed complex social behaviors and sophisticated methods of temperature regulation. And in the oceans, marine ecosystems reached levels of complexity and diversity that wouldn't be seen again for millions of years. But all of this incredible evolutionary progress was about to be swept away by forces so powerful and destructive that they would fundamentally alter the chemistry of the entire planet. The Great Dying was approaching, and when it arrived, it would make all previous extinctions look like minor setbacks in comparison. The survivors of this ultimate catastrophe would inherit a world so dramatically changed that it might as well have been an alien planet. The recovery would take millions of years and would ultimately give rise to entirely new groups of animals, including the dinosaurs that would dominate the Earth for the next 160 million years. But that incredible story of destruction and rebirth was still to come. For now, life was enjoying one of its most creative and diverse periods, completely unaware that the greatest test of survival in Earth's history was building beneath their feet. The volcanic forces that would soon reshape the world were gathering strength in the depths of the planet, preparing to unleash destruction on a scale that would dwarf everything that had come before. The countdown to the Great Dying had begun, and nothing would ever be the same again. Deep beneath the supercontinent Pangaea, in a region that would one day become Siberia, something monstrous was stirring. Far below the thriving ecosystems and diverse communities of life on the surface, an enormous pool of magma was growing larger and more unstable with each passing millennium. This wasn't just another volcanic system. This was a geological nightmare that contained enough molten rock to fundamentally alter the entire planet. The pressure building in this underground chamber was beyond anything that had ever occurred in Earth's history. The magma wasn't just hot. It was superheated to temperatures that could vaporize solid rock instantly. And it was rising, slowly but inexorably, toward the surface where millions of unsuspecting creatures were living out their daily lives in what they thought was a stable, predictable world. For thousands of years, there were subtle warning signs that something extraordinary was happening deep underground. Small earthquakes rippled through the crust as the rising magma cracked and fractured the rock above it. Hot springs began appearing in areas where they had never existed before, and in some regions, the ground itself began to warm as the molten rock approached the surface. But these signs were too subtle and too gradual for the life forms of the time to recognize as harbingers of doom. The early reptiles continued their evolutionary experiments, developing new forms and adaptations. The marine ecosystems continued to flourish in the warm, shallow seas, and the forests continued their patient work of transforming the atmosphere and landscape. Then, roughly 252 million years ago, the Earth's crust finally gave way. The eruption that began in Siberia was unlike anything that had ever happened on our planet. This wasn't a single volcanic explosion. It was the beginning of a volcanic catastrophe that would continue for over 1 million years. Imagine lava flows so massive that they could cover an entire continent. Picture volcanic gases pouring into the atmosphere in quantities that would fundamentally alter the chemistry of the air and oceans. The scale of this eruption defies comprehension. The lava flows, known today as the Siberian Traps, eventually covered an area larger than Western Europe in molten rock that was, in some places, over 1 mile thick. But the lava itself was just the beginning of this planetary catastrophe. The real devastation came from the gases that accompanied the eruption. Massive quantities of carbon dioxide poured into the atmosphere, creating a greenhouse effect so intense that global temperatures began rising at an unprecedented rate. Sulfur compounds mixed with water vapor to create acid rain that could dissolve limestone and burn through plant tissue. And perhaps most deadly of all, the eruptions released enormous amounts of toxic gases that poisoned the air and water across the entire planet. The effects of this volcanic apocalypse were felt almost immediately. In the oceans, the rising temperatures and changing chemistry created conditions that were lethal to most marine life. Coral reefs, which had been among the most diverse and productive ecosystems on Earth, began dying en masse as the water became too hot and too acidic for them to survive. The tiny organisms that formed the base of the marine food web were among the first casualties. These microscopic creatures, which had been producing oxygen and supporting entire ecosystems for hundreds of millions of years, simply couldn't survive in the rapidly changing conditions. As they died off, the effects rippled up through every level of the food chain, causing a cascade of extinctions that swept through the oceans like a plague. On land, the situation was equally catastrophic. The massive amounts of carbon dioxide released by the volcanoes created a greenhouse effect so severe that temperatures soared to levels that most life forms couldn't tolerate. Plants, which had been thriving in the warm but stable conditions of the late Permian, found themselves in an environment where the air itself was becoming toxic. The acid rain that resulted from the volcanic emissions was particularly devastating to plant life. This wasn't just mildly acidic precipitation. This was rain that could strip leaves from trees and dissolve the very soil that plants depended on for nutrients. Entire forests began dying, leaving vast areas of the continents as barren wastelands where nothing could grow. As the plant life collapsed, so did the animals that depended on it. Herbivorous reptiles, some of which had grown to enormous sizes during the prosperity of the Permian, found themselves in a world where food was becoming increasingly scarce. Many of these creatures had evolved to be specialists, feeding on particular types of plants that were now disappearing from the landscape. The predators that had fed on these herbivores soon followed them into extinction. The carefully balanced ecosystems that had taken millions of years to develop were collapsing in a matter of decades. Creatures that had been apex predators found themselves scavenging for scraps in a world where the abundance they had known was rapidly becoming a memory. But the volcanic catastrophe had even more devastating effects in store. As the eruptions continued year after year, decade after decade, they began to fundamentally alter the chemistry of the oceans themselves. The massive amounts of carbon dioxide dissolving into seawater made the oceans increasingly acidic, creating conditions that were lethal to any creature with a shell or skeleton made of calcium carbonate. This ocean acidification was particularly devastating to marine invertebrates. Creatures like brachiopods, which had been among the most successful animals in Earth's history, found that they simply couldn't build or maintain their shells in the new chemical environment. Their protective coverings began dissolving, leaving them vulnerable to predators and environmental stresses. The rising temperatures also had another deadly effect. They reduced the amount of oxygen that could dissolve in seawater. As the oceans warmed, vast areas became oxygen-depleted dead zones where complex life simply couldn't survive. Fish and other marine animals found themselves suffocating in waters that had once been rich with the gas they needed to breathe. Perhaps most terrifyingly, the changing ocean chemistry created perfect conditions for certain types of bacteria that produced hydrogen sulfide, a gas that is toxic to most complex life forms. These bacteria began proliferating in the oxygen-depleted waters, producing clouds of poisonous gas that rose into the atmosphere and spread across the planet. The hydrogen sulfide didn't just poison the air, it also attacked the ozone layer, further reducing the planet's protection from harmful solar radiation. This created yet another stress on the already struggling ecosystems, as increased ultraviolet radiation damaged the DNA of plants and animals that were already fighting for survival in the increasingly hostile environment. As the volcanic eruptions continued, the effects became increasingly severe and far-reaching. The combination of rising temperatures, acid rain, ocean acidification, oxygen depletion, and toxic gases created what scientists call a perfect storm of environmental destruction. It was as if the Earth itself was trying to sterilize its surface, eliminating life with a combination of heat, poison, and radiation. The few creatures that managed to survive this initial onslaught found themselves in a world that bore no resemblance to the one their ancestors had known. The lush forests were gone, replaced by barren landscapes dotted with the skeletal remains of dead trees. The diverse marine ecosystems had been reduced to simple communities of bacteria and the hardiest microorganisms. Yet even in this hellish environment, some life persevered. Small, adaptable creatures that could tolerate extreme conditions began to eke out an existence in the ruins of the old world. These survivors weren't the largest or most impressive animals of their time, but they possessed something even more valuable: the ability to adapt quickly to changing conditions. Among these survivors were small, mammal-like reptiles that had developed sophisticated methods of temperature regulation and efficient metabolisms that allowed them to survive on limited food resources. These humble creatures, no larger than modern rats, would prove to be among the most important survivors of the Great Dying, as their descendants would eventually give rise to all modern mammals, including ourselves. The Great Dying, as this extinction event came to be known, was the most severe test that life on Earth had ever faced. By the time the worst of the volcanic activity finally subsided, over 90% of all marine species and 70% of terrestrial species had vanished forever. It was the closest that complex life had ever come to complete extinction, and it would take millions of years for biodiversity to recover to pre-extinction levels. But recover it did, and in ways that would set the stage for the next great chapter in Earth's story, the age of dinosaurs. The recovery from the Great Dying was unlike anything our planet had ever witnessed before. As the volcanic fires finally began to subside and the toxic clouds slowly cleared from the atmosphere, Earth resembled a blank canvas, waiting for evolution's next masterpiece. But this wasn't going to be a simple restoration of what had come before. The survivors of this ultimate catastrophe were about to embark on evolutionary experiments so radical and successful that they would reshape life on our planet for the next 200 million years. Picture the world roughly 240 million years ago, as we enter what geologists call the Triassic period. The supercontinent Pangaea stretched from pole to pole like a massive scar across the planet's surface. The climate was hot and dry, with vast deserts covering much of the interior, while humid coastal regions provided the only refuges where complex life could truly flourish. The few species that had survived the Permian catastrophe found themselves in a world of unprecedented opportunity. With over 90% of their competitors eliminated, these hardy survivors could explore ecological niches that had been occupied for hundreds of millions of years. It was like inheriting a mansion after everyone else had moved out, except this mansion was an entire planet. Among the most successful of these survivors were small reptiles that had developed something revolutionary during the harsh conditions of the extinction: improved methods of breathing. While their ancestors had struggled with the low oxygen conditions created by the volcanic catastrophe, these creatures had evolved more efficient lungs and circulatory systems that gave them a crucial advantage in the New World. These adaptations might seem minor, but they would prove to be absolutely game-changing. Better breathing meant these reptiles could be more active, travel longer distances, and compete more effectively for the limited resources available in the post-extinction landscape. And as the climate began to stabilize and plant life slowly returned, these advantages would compound into something extraordinary. The early Triassic world was dominated by creatures that looked like bizarre crosses between modern crocodiles and lizards. Some were small and agile, darting through the sparse vegetation in search of insects and other small prey. Others grew to impressive sizes, becoming the apex predators of their recovering ecosystems. But all of them shared certain characteristics that would prove crucial for the evolutionary innovations to come. One group of these survivors began developing something that would change the course of life on Earth forever: more sophisticated parental care. Instead of simply laying eggs and abandoning them like most reptiles, some species began actively protecting and caring for their young. This might not sound revolutionary, but it was actually a crucial step toward one of the most important developments in vertebrate evolution. These early experiments in parental care led to the evolution of creatures that could regulate their body temperature more effectively and maintain higher activity levels than their cold-blooded relatives. Some developed elaborate crests and sails that helped them control their internal temperature, while others evolved the first primitive forms of insulation that would eventually become fur and feathers. But perhaps the most significant development was happening in a group of reptiles that were becoming increasingly bird-like in their anatomy and behavior. These creatures, which scientists call archosaurs, were developing longer legs positioned directly beneath their bodies rather than sprawling out to the sides like traditional reptiles. This seemingly simple change in posture would have profound implications for their descendants. The upright posture allowed these archosaurs to move more efficiently and sustain higher activity levels than their sprawling relatives. They could run faster, travel farther, and compete more effectively for resources. But more importantly, this new body plan was perfectly suited for the evolution of something that had never existed before on our planet. Truly gigantic land animals. As the Triassic period progressed and ecosystems continued to recover from the Great Dying, some of these archosaurs began growing to sizes that dwarfed anything that had come before. The first dinosaurs were relatively small creatures, no larger than modern dogs, but they possessed all the anatomical innovations that would eventually allow their descendants to become the largest land animals in Earth's history. Meanwhile, life in the oceans was also undergoing dramatic changes. The few marine species that had survived the Permian extinction were diversifying rapidly, filling the empty ecological niches left by their extinct relatives. New types of marine reptiles evolved that were perfectly adapted for life in the water, with streamlined bodies, powerful flippers, and sophisticated sensory systems. Some of these marine reptiles grew to enormous sizes, becoming the apex predators of the recovering ocean ecosystems. Creatures like ichthyosaurs evolved bodies that were remarkably similar to modern dolphins and sharks, demonstrating how evolution often finds similar solutions to similar environmental challenges. These marine giants could dive to great depths, swim at incredible speeds, and hunt prey that ranged from small fish to other large marine reptiles. The diversity of marine life during the Triassic was truly remarkable. Coral reefs began to recover and diversify, creating complex three-dimensional habitats that supported countless species of fish, invertebrates, and marine reptiles. New types of sharks evolved that were even more efficient predators than their Paleozoic ancestors. And in the shallow coastal waters, entirely new ecosystems developed that would serve as nurseries for the next generation of marine innovations. But even as life was flourishing in this post-extinction world, the Earth was far from stable. The same geological forces that had created Pangaea were continuing to reshape the planet's surface, and the stresses building within the supercontinent were approaching another breaking point. Deep beneath the surface, magma was once again beginning to accumulate in massive chambers, setting the stage for another volcanic catastrophe. The first signs of this impending disaster began appearing roughly 200 million years ago. Small earthquakes rippled through the crust as underground pressures built to dangerous levels. In some regions, the ground began to crack and vent gases that hinted at the inferno building below. But life on the surface continued its remarkable recovery, completely unaware that another test of survival was approaching. When the crisis finally erupted, it would split Pangaea apart and create the Atlantic Ocean basin in one of the most violent geological events in Earth's history. But unlike the slow-burning catastrophe of the Permian extinction, this would be a relatively brief but incredibly intense period of destruction that would reshape both the physical geography of our planet and the evolutionary trajectory of life itself. The Triassic-Jurassic extinction, as this event came to be known, would eliminate many of the large reptiles that had dominated the early recovery from the Great Dying. But it would also clear the way for a group of survivors that would go on to achieve something unprecedented in the history of life on Earth. They would become the most successful large animals our planet had ever seen. The age of dinosaurs was about to begin, and with it would come innovations in size, behavior, and ecology that would make the Triassic recovery look like a modest warm-up act. These remarkable creatures would dominate terrestrial ecosystems for over 160 million years, evolving into forms so diverse and spectacular that they continue to capture our imagination today. But before we can explore that incredible story, we need to witness the catastrophe that made it possible. The forces building beneath Pangaea were reaching critical mass, and when they finally erupted, they would literally tear the supercontinent apart and create the geographic foundation of the modern world. The volcanic eruptions that ended the Triassic period began with a series of massive explosions that split the supercontinent along what would eventually become the Mid-Atlantic Ridge. Unlike the prolonged volcanic nightmare of the Permian extinction, this catastrophe unfolded over a relatively brief period of perhaps 50,000 years. But what it lacked in duration, it more than made up for in sheer intensity. Imagine lava flows that could cover entire states in molten rock within a matter of weeks. Picture volcanic explosions so powerful that they hurled billions of tons of ash and gas into the stratosphere, blocking out the sun and plunging the planet into a volcanic winter. The energy released during this brief period was equivalent to millions of nuclear weapons detonating simultaneously across multiple continents. The immediate effects were catastrophic for many of the large reptiles that had been thriving in the Triassic ecosystems. These creatures, which had evolved during the relatively stable conditions of the early recovery period, were poorly adapted to survive the rapid environmental changes triggered by the volcanic eruptions. Many of the apex predators and large herbivores that had dominated the post-Permian world vanished within a few thousand years. But hidden among the chaos and destruction, a group of small, agile reptiles was not just surviving, but actually thriving in the changing conditions. These were the early dinosaurs, and they possessed a combination of traits that made them perfectly suited for life in the unstable world created by the volcanic catastrophe. Their efficient respiratory systems allowed them to remain active even when atmospheric conditions became challenging. Their upright posture and efficient locomotion enabled them to travel long distances in search of food and suitable habitat. And perhaps most importantly, their relatively small size and adaptable behavior allowed them to exploit resources that were inaccessible to their larger, more specialized competitors. As the volcanic activity finally subsided and environmental conditions began to stabilize, these dinosaur survivors found themselves in a world that was perfectly suited for their particular combination of traits. The breakup of Pangaea had created new climate patterns that were more varied and dynamic than the relatively uniform conditions of the supercontinent period. This climatic diversity provided opportunities for evolutionary experimentation on an unprecedented scale. The dinosaurs seized these opportunities with remarkable success. Within just a few million years, of the Triassic-Jurassic extinction, they had diversified into an incredible array of forms that exploited virtually every available ecological niche. Some remained small and agile, evolving into efficient predators that could hunt everything from insects to small mammals. Others began growing to enormous sizes, becoming the largest land animals in Earth's history. But perhaps most remarkably, some dinosaurs began developing entirely new innovations that had never been seen before in vertebrate evolution. The evolution of feathers, initially for insulation and display rather than flight, opened up possibilities for behavioral complexity and eventually aerial locomotion that would revolutionize life on Earth. The success of the dinosaurs during the Jurassic and Cretaceous periods was truly extraordinary. They evolved into forms that ranged from tiny bird-like creatures no larger than sparrows to massive sauropods that could weigh as much as 10 elephants. Some became sophisticated pack hunters with complex social behaviors, while others developed defensive strategies involving elaborate armor plating and formidable weapons. The diversity of dinosaur species was staggering. In the forests, long-necked sauropods browsed on vegetation that grew over 100 feet above the ground. In the open plains, herds of ornithopods migrated across vast distances in search of seasonal food sources, and stalking through both environments were predators that ranged from small, intelligent hunters to massive apex predators that could take down prey many times their own weight. Meanwhile, in the skies above these terrestrial giants, the first flying dinosaurs were beginning their conquest of the aerial realm. The evolution of powered flight represented one of the most significant innovations in the history of life, opening up three-dimensional habitat space that had previously been accessible only to insects and other small invertebrates. These early flying dinosaurs, which we now recognize as the first birds, were not just passive gliders, but active, powered flyers capable of complex aerial maneuvers. They could escape ground-based predators, access food sources that were unavailable to terrestrial animals, and eventually migrate across vast distances to exploit seasonal resources. The oceans during this period were equally spectacular, dominated by marine reptiles that had evolved to enormous sizes and remarkable levels of specialization. Massive marine crocodiles patrolled the shallow seas, while long-necked plesiosaurs and streamlined ichthyosaurs ruled the deeper waters. Some of these marine giants grew to lengths that rivaled modern blue whales, making them among the largest predators that have ever existed. But even as the dinosaurs were reaching the peak of their success, forces were already in motion that would bring their remarkable reign to an abrupt and catastrophic end. Deep in space, a mountain-sized asteroid was following an orbit that would eventually intersect with Earth's path around the sun. This cosmic projectile, traveling at speeds of several miles per second, was completely invisible to the thriving ecosystems below, but represented a threat more immediate and devastating than any volcanic eruption. The story of what happened when this asteroid finally struck our planet is one of the most dramatic and well-documented catastrophes in Earth's history. But it's also a story of survival, adaptation, and evolutionary opportunity that would ultimately lead to the rise of mammals and eventually our own species. The impact that ended the age of dinosaurs was more than just a cosmic accident. It was a pivotal moment that redirected the entire course of evolution on our planet. Without this catastrophic event, the small furry creatures that were our distant ancestors might never have had the opportunity to diversify and eventually give rise to the complex ecosystems and intelligent life that characterize our modern world. As we prepare to explore this final mass extinction and its aftermath, we're about to witness how a single moment of cosmic violence could completely reshape the biological destiny of an entire planet. The age of dinosaurs was ending, but the age of mammals was about to begin, setting the stage for the emergence of creatures capable of not just surviving mass extinctions, but of studying and understanding them. The story of how our own lineage emerged from the ashes of this cosmic catastrophe is perhaps the most remarkable tale of resilience and opportunity in the entire history of life on Earth. The late Cretaceous world was a planet of giants where colossal creatures ruled landscapes that would seem utterly alien to our modern eyes. Picture yourself standing in what would one day become Montana or Alberta, surrounded by forests of towering conifers and flowering plants that had only recently evolved. The air was thick and humid, heavy with the scent of unfamiliar blooms and the musky odor of massive reptilian bodies moving through the undergrowth. This was a world where Tyrannosaurus rex, that iconic apex predator, stalked through coastal plains with footsteps that could be felt from miles away. These weren't the sluggish, cold-blooded monsters of old Hollywood movies. Recent discoveries suggest they were active, possibly warm-blooded hunters capable of surprising bursts of speed and equipped with bone-crushing jaws that could exert pressure equivalent to the weight of a small truck. But even the mighty T-Rex was just one player in an ecosystem of unprecedented complexity and scale. Massive herds of duck-billed hadrosaurs migrated across vast distances, their elaborate crests serving as living trumpets that could produce haunting calls audible for miles. These weren't simple, primitive creatures. They possessed sophisticated social behaviors, complex communication systems, and dental batteries that could process even the toughest plant material with remarkable efficiency. In the coastal waters, marine reptiles had evolved to sizes that challenged the laws of physics. Mosasaurs, gigantic marine lizards with flippers instead of legs, patrolled the shallow seas like living submarines. Some species reached lengths of over 50 feet, making them larger than most modern whales. Their powerful jaws, lined with razor-sharp teeth, could crush ammonites and smaller marine reptiles with devastating efficiency. Swimming alongside these apex predators were creatures that seemed to belong in a fever dream. Enormous sea turtles, some with shells over 12 feet long, glided through the warm waters. Massive marine crocodiles, far larger than any modern species, lurked in coastal swamps and river deltas. And in the deeper waters, long-necked plesiosaurs moved with surprising grace despite their enormous size, using 4 flipper-like limbs to propel themselves through their aquatic realm. The skies above this prehistoric world were equally spectacular. Pterosaurs had reached the absolute limits of what was possible for flying animals. Quetzalcoatlus, with its wingspan approaching that of a small airplane, soared over the landscape like a living glider. These weren't just oversized bats. They were sophisticated flying machines with complex air sac systems similar to those found in modern birds, allowing them to remain airborne despite their enormous size. But perhaps most remarkably, the first true birds were beginning to diversify and compete with their pterosaur cousins for control of the skies. These early avians had evolved from small, feathered dinosaurs and retained many reptilian characteristics, including teeth and long bony tails. Yet they possessed something that would prove crucial for their survival in the catastrophe to come. They were small, adaptable, and capable of exploiting a wide variety of food sources. Meanwhile, in the shadows of these giants, small mammals were quietly going about their lives in ways that would prove prophetic. These creatures, no larger than modern rats or possums, had evolved sophisticated strategies for survival that included enhanced sensory systems, efficient metabolisms, and most importantly, the ability to care for their young in ways that gave them crucial advantages during times of environmental stress. These early mammals weren't just surviving, they were innovating. Some had developed the ability to glide between trees using flaps of skin stretched between their limbs. Others had evolved specialized teeth for processing different types of food, from insects to seeds to small vertebrates. And perhaps most significantly, they had developed reproductive strategies that allowed them to raise their young to maturity even under challenging conditions. But even as life was flourishing with unprecedented diversity and complexity, cosmic forces were converging that would bring this golden age to a sudden and catastrophic end. Somewhere in the asteroid belt between Mars and Jupiter, a chunk of rock and metal, roughly 6 miles across, was following an orbit that had remained stable for millions of years. This asteroid, composed of materials left over from the formation of the solar system itself, was completely unremarkable, except for one crucial detail. Its trajectory was slowly but inevitably bringing it into collision course with Earth. The gravitational interactions that nudged this cosmic projectile toward our planet were subtle and complex, involving the combined influences of Jupiter, Mars, and countless smaller bodies in the asteroid belt. For millions of years, these forces had been working to alter the asteroid's orbit by tiny amounts, gradually shifting its path until it pointed directly at the third planet from the sun. As this mountain-sized bullet hurtled through space at speeds approaching 20 miles per second, life on Earth continued its daily routines, completely unaware of the approaching doom. Dinosaurs continued their evolutionary experiments, developing new forms and behaviors. Marine reptiles explored the depths of ancient seas, and early mammals went about their nocturnal activities, raising their young and adapting to life in a world dominated by giants. The final approach of the asteroid was invisible to the creatures below. Even if any of them had possessed the ability to detect objects in space, the incoming projectile would have been nothing more than a faint point of light, indistinguishable from the countless stars that filled the night sky. There were no warning signs, no gradual buildup of environmental stress, no opportunity for life to prepare for what was about to happen. When the asteroid finally entered Earth's atmosphere, it created a fireball brighter than the sun that was visible from thousands of miles away. The entry alone released energy equivalent to billions of nuclear weapons, heating the air to temperatures that could vaporize solid rock. But this spectacular light show was just the opening act of a cosmic catastrophe that would unfold over the course of several hours and reshape the entire planet. The impact itself occurred in what is now the Yucatan Peninsula in Mexico, in shallow tropical seas that were teeming with marine life. When the asteroid struck the seafloor, it released energy equivalent to over 1 billion atomic bombs detonating simultaneously. The explosion vaporized not just the asteroid itself, but enormous quantities of rock, water, and living tissue, hurling this superheated material high into the atmosphere and beyond. The immediate effects were beyond anything that complex life had ever experienced. The impact created a crater over 100 miles across and temporarily excavated a cavity in the Earth's crust that was deeper than the height of Mount Everest. Shock waves radiating outward from the impact site triggered earthquakes more powerful than any recorded in human history, causing massive landslides and ground fractures across multiple continents. But the seismic devastation was just the beginning. Within minutes of the impact, a wall of superheated debris began raining down across the entire planet. This wasn't ordinary meteorite shower. This was a global firestorm of molten rock droplets that had been blasted into space by the impact and were now falling back to Earth like deadly hail. The energy released by this falling debris was so intense that it heated the atmosphere to temperatures that could ignite vegetation across entire continents. For creatures living anywhere near the impact site, death was instantaneous. The blast wave vaporized everything within hundreds of miles of ground zero, while the thermal pulse ignited fires that spread across vast areas of North and Central America. Marine life in the Gulf of Mexico was boiled alive as the impact converted enormous quantities of seawater into superheated steam. But even creatures living on the opposite side of the planet weren't safe from the immediate effects of the impact. The seismic waves generated by the collision traveled through the Earth's core and converged on the antipodal point, creating massive volcanic eruptions and ground fractures in what is now India. These secondary effects added their own contribution to the global catastrophe, spewing additional gases and particles into an atmosphere that was already choking with debris. As the hours passed, the global effects of the impact became increasingly severe. The enormous quantities of dust, ash, and vaporized rock that had been hurled into the stratosphere began to spread around the entire planet, creating a thick blanket that blocked out the sun's light. Within days, the Earth was plunged into a darkness deeper than any natural night, a condition that would persist for months. This impact winter was devastating to the ecosystems that had evolved under the assumption that sunlight would always be available. Plants, which formed the foundation of virtually every food web on the planet, began dying en masse as photosynthesis became impossible. The effects rippled up through every level of the ecosystem, from the smallest herbivores to the largest predators. The large dinosaurs that had dominated terrestrial ecosystems for over 160 million years were particularly vulnerable to these rapidly changing conditions. Their enormous size, which had been an advantage during normal times, became a fatal liability when food sources began disappearing. creatures that required hundreds of pounds of vegetation or meat per day simply couldn't survive in a world where primary productivity had collapsed. The massive marine reptiles faced similar challenges as the oceanic food webs collapsed. The tiny planktonic organisms that formed the base of marine ecosystems were among the first casualties of the impact winter, dying off in enormous numbers as the lack of sunlight made photosynthesis impossible. Without these microscopic producers, the entire marine ecosystem began to unravel from the bottom up. But even as the giants were dying, some creatures possessed characteristics that allowed them to survive in this hellish new world. Small mammals, with their efficient metabolisms and ability to survive on limited food resources, found themselves with a crucial advantage. Their underground burrows provided protection from the extreme temperature fluctuations that characterized the post-impact environment, while their varied diets allowed them to exploit whatever food sources remained available. Birds, those feathered descendants of dinosaurs, also possessed traits that proved crucial for survival. Their small size meant they required relatively little food, while their ability to fly allowed them to search vast areas for whatever resources might be available. Many species could also enter states of reduced metabolic activity, essentially hibernating through the worst of the environmental crisis. Some reptiles also managed to survive, particularly those species that were already adapted to harsh environmental conditions. Crocodiles and their relatives, with their slow metabolisms and ability to survive for months without food, weathered the crisis in rivers and swamps that were less affected by the global catastrophe. Turtles, protected by their shells and capable of entering dormant states, also proved remarkably resilient to the changing conditions. The recovery from this cosmic catastrophe was unlike anything that had occurred during previous mass extinctions. Unlike the gradual environmental changes that had characterized earlier crises, the asteroid impact created conditions that changed almost overnight and then persisted for extended periods. This meant that survival depended not just on tolerance for extreme conditions, but also on the ability to adapt quickly to rapidly changing circumstances. As the impact winter gradually ended and sunlight began to return to the Earth's surface, the survivors found themselves in a world that had been fundamentally transformed. The great forests of conifers that had dominated many landscapes were gone, replaced by open areas covered with ferns and other pioneer plants. The complex marine ecosystems that had supported enormous diversity were reduced to simple communities of hardy survivors. But this devastated world also represented an unprecedented opportunity for the creatures that had managed to survive the catastrophe. With the dominant groups eliminated, ecological niches that had been occupied for millions of years were suddenly available for colonization. The small mammals that had lived in the shadows of the dinosaurs could now explore habitats and lifestyles that had previously been impossible. The evolutionary response to this opportunity was swift and dramatic. Within just a few million years of the impact, mammals had begun diversifying into forms that would have been unimaginable during the age of dinosaurs. Some remained small and secretive, but others began growing to sizes that approached or even exceeded those of some dinosaurs. The most successful of these early experiments involved mammals that developed new feeding strategies and locomotion methods. Some evolved into efficient predators that could hunt the various reptiles and other animals that had survived the extinction. Others became specialized herbivores that could process the new types of vegetation that were beginning to dominate the recovering landscapes. Perhaps most remarkably, some mammals began developing intelligence and social behaviors that far exceeded anything that had been seen in previous groups. These cognitive innovations allowed them to solve complex problems, communicate sophisticated information to other members of their species, and adapt to changing conditions in ways that gave them enormous advantages over their competitors. The birds that survived the extinction also underwent remarkable evolutionary radiation, diversifying into forms that exploited virtually every available ecological niche. Some became powerful predators that could take the place of the extinct carnivorous dinosaurs. Others evolved into specialized seed eaters, fruit eaters, and nectar feeders that help pollinate the flowering plants that were beginning to dominate many ecosystems. In the oceans, the recovery was equally dramatic, but followed different patterns. The extinction of the large marine reptiles had eliminated most of the apex predators from marine ecosystems, creating opportunities for other groups to evolve into these vacant roles. Sharks, which had survived the extinction with relatively little change, began diversifying into new forms that could exploit the available resources. Marine mammals, descended from small land mammals that had returned to the water, began their own remarkable evolutionary journey. These early experiments in aquatic mammalian life would eventually give rise to whales, dolphins, and other marine mammals that would become some of the most intelligent and socially complex animals on Earth. The flowering plants that had been beginning to diversify during the Cretaceous also seized the opportunities created by the extinction. With many of the large herbivorous dinosaurs eliminated, these plants could explore new strategies for reproduction and dispersal. The coevolution between flowering plants and their animal pollinators became one of the most important partnerships in the history of life, creating the diverse and productive ecosystems that characterize much of our modern world. As millions of years passed, the Earth gradually developed the characteristics that we recognize today. The continents continued their slow drift toward their current positions, while climate patterns became increasingly complex and varied. Mountain ranges rose and fell, ice ages came and went, and life continued its patient work of adaptation and innovation. The mammals that had inherited the Earth from the dinosaurs continued to diversify and evolve, eventually giving rise to an incredible array of forms. Some became enormous, like the massive ground sloths and saber-toothed cats that would dominate many ecosystems. Others remained small and agile, developing increasingly sophisticated sensory systems and cognitive abilities. Among these diverse mammalian experiments, one lineage began developing characteristics that would prove to be truly revolutionary. These early primates possessed enhanced vision, dexterous hands, and increasingly complex brains that allowed them to navigate the three-dimensional world of the forest canopy with remarkable skill. The evolutionary journey from these early primates to modern humans would take tens of millions of years, and involve countless intermediate forms, each adapted to specific environmental conditions and challenges. But the foundation for this remarkable lineage was laid in the aftermath of the cosmic catastrophe that ended the age of dinosaurs. The asteroid impact that eliminated the non-avian dinosaurs was more than just a random cosmic accident. It was a pivotal moment that redirected the entire course of evolution on our planet. Without this catastrophic event, the small mammals that were our distant ancestors might never have had the opportunity to diversify and explore the ecological possibilities that eventually led to the emergence of intelligence, culture, and technology. As we stand today on the brink of what many scientists believe may be a sixth mass extinction, the lessons from these ancient catastrophes become increasingly relevant. Each of the previous 5 mass extinctions was triggered by different causes, from cosmic impacts to massive volcanic eruptions to gradual climate changes. But they all shared certain characteristics. They occurred relatively rapidly on geological timescales. They eliminated dominant groups while favoring other survivors. And they ultimately led to evolutionary innovations that created new possibilities for life. The current biodiversity crisis differs from previous mass extinctions in that it's being caused by the activities of a single species rather than by cosmic or geological forces. But the fundamental patterns may be similar. Rapid environmental change, the elimination of species that can't adapt quickly enough, and opportunities for survivors to exploit vacant ecological niches. Understanding how life has responded to previous mass extinctions provides crucial insights into the resilience and adaptability of biological systems. It shows us that while mass extinctions are devastating in the short term, they also serve as catalysts for evolutionary innovation and the emergence of new forms of life. The survivors of these catastrophes aren't necessarily the largest or most dominant species, but rather those that possess the flexibility and adaptability needed to thrive under rapidly changing conditions. The story of the 5 great mass extinctions is ultimately a story about the incredible resilience of life itself. Despite facing cosmic catastrophes, massive volcanic eruptions, climate changes, and toxic atmospheric conditions, life has not only survived, but has repeatedly bounced back to achieve even greater diversity and complexity than before. Each extinction event cleared away established ecosystems and dominant species, creating opportunities for evolutionary experiments that would have been impossible under normal conditions. The mammals that inherited the Earth from the dinosaurs that rose from the ashes of the Permian extinction, and the early vertebrates that survived the Ordovician catastrophe all represent examples of how life can seize the opportunities created by global disasters. As we face the challenges of the modern world, including climate change, habitat destruction, and the ongoing loss of biodiversity, the lessons from deep time remind us that life is both fragile and remarkably resilient. The key to survival, whether for individual species or entire ecosystems, lies not in size or dominance, but in adaptability, flexibility, and the ability to exploit new opportunities as they arise. The Earth has survived 5 mass extinctions and emerged each time with life forms more diverse and complex than before. While we must do everything in our power to prevent a 6th mass extinction, the history of our planet also teaches us that life finds ways to persist and evolve even under the most challenging conditions imaginable. The story of mass extinctions is far from over as we continue to study these ancient catastrophes and their aftermath. We gain new insights into the processes that shape life on our planet and the factors that determine which species survive and which disappear forever. This knowledge becomes increasingly important as we work to understand and address the environmental challenges facing our world today. The question that haunts scientists today is whether we're witnessing the opening act of a 6th mass extinction, one driven not by cosmic collisions or volcanic fury, but by the actions of a single species that emerged from the ashes of that final catastrophe. But to understand where we might be heading, we need to examine what makes this potential 6th extinction fundamentally different from everything that came before. Think about this for a moment. Every previous mass extinction was triggered by forces completely beyond the control of life itself. Gamma ray bursts from dying stars, massive volcanic eruptions from deep within the Earth, asteroid impacts from the depths of space. These were external shocks that hit biological systems like cosmic hammers striking an anvil. Life had no choice but to endure whatever the universe threw at it. But something unprecedented happened after that asteroid struck the Yucatan Peninsula 66 million years ago. Among the small furry survivors scurrying through the post-impact wasteland were creatures that would eventually develop something that had never existed before in Earth's 4 billion year history. The ability to consciously alter their environment on a planetary scale. The mammals that inherited the dinosaurs' world didn't just adapt to their surroundings, they began actively reshaping them. At first, this was nothing more than the normal activities of any successful species. They dug burrows, built nests, created trails through the landscape. But as millions of years passed and these mammals diversified into an incredible array of forms, some lineages began developing capabilities that would prove to be absolutely revolutionary. Picture the world roughly 55 million years ago, during what scientists call the Paleocene-Eocene thermal maximum. This was a period of rapid global warming triggered by massive releases of carbon dioxide into the atmosphere, possibly from volcanic activity or the sudden melting of methane hydrates on the ocean floor. Temperatures soared, ice caps melted completely, and tropical forests extended all the way to the polar regions. Most of the mammals living during this time responded to the changing climate exactly as life had always responded to environmental challenges. They adapted, migrated, or went extinct. Some species moved toward the poles to escape the heat, while others evolved new physiological mechanisms for dealing with higher temperatures. It was a classic example of how life responds to external environmental pressures. But hidden among these typical evolutionary responses, something extraordinary was beginning to emerge. Some mammalian lineages were developing enhanced cognitive abilities that allowed them to solve problems, manipulate objects, and pass information between generations in ways that had never been seen before. These early experiments in intelligence were subtle and limited, but they represented the first stirrings of a completely new force in Earth's history. The primates that emerged during this period possessed a combination of traits that would prove to be revolutionary. Enhanced vision allowed them to navigate complex three-dimensional environments with remarkable precision. Dexterous hands gave them the ability to manipulate objects in sophisticated ways. And most importantly, enlarged brains provided the computational power needed to process complex information and make decisions based on past experience. These cognitive innovations might seem modest compared to the massive physical adaptations that had characterized previous evolutionary breakthroughs. After all, what's a slightly larger brain compared to the evolution of flight, or the development of photosynthesis, or the transition from water to land? But these mental enhancements were laying the groundwork for something that would fundamentally alter the relationship between life and environment on our planet. As these early primates diversified and spread across the warming world, they began developing increasingly sophisticated behaviors. Some species learned to use tools, employing sticks and stones to extract food from difficult-to-reach places. Others developed complex social structures that allowed them to share information and coordinate group activities. And a few began showing signs of cultural transmission, passing learned behaviors from one generation to the next through observation and imitation rather than genetic inheritance. The significance of this cultural transmission cannot be overstated. For the first time in Earth's history, a species was developing the ability to accumulate knowledge and pass it on to future generations without waiting for genetic mutations to spread through populations. This meant that adaptive innovations could spread much faster than traditional evolutionary processes allowed, giving these creatures an unprecedented ability to respond to environmental challenges. Meanwhile, the climate was continuing to fluctuate in ways that provided perfect conditions for testing these new cognitive abilities. The greenhouse conditions of the early Eocene gradually gave way to cooler, more variable climate patterns as carbon dioxide levels dropped and ice caps began forming at the poles. These changing conditions created a complex mosaic of environments that rewarded flexibility, adaptability, and problem-solving skills. The mammals that possessed these enhanced cognitive abilities found themselves with significant advantages in this changing world. They could remember the locations of seasonal food sources, anticipate environmental changes based on past experience, and develop new strategies for dealing with novel challenges. Most importantly, they could share this information with other members of their species, creating a collective knowledge base that grew more sophisticated with each passing generation. But even these remarkable cognitive innovations were still operating within the traditional framework of species adapting to their environment. These early primates were using their intelligence to find food, avoid predators, and raise their young more effectively, but they weren't yet capable of fundamentally altering the ecosystems around them. They were still playing by the same rules that had governed life for billions of years. The breakthrough that would change everything came much later, in a lineage of African primates that had been experimenting with increasingly sophisticated tool use and social cooperation. Around 7 million years ago, these creatures began developing something that would prove to be the most important innovation in the history of life on Earth: the ability to modify their environment intentionally and systematically. The early hominins that emerged during this period looked quite different from modern humans, but they possessed the cognitive foundations that would eventually lead to technological civilization. They could make and use tools, control fire, and engage in complex social behaviors that required sophisticated communication and planning. Most importantly, they had begun to see themselves as separate from and capable of controlling the natural world around them. This shift in perspective was absolutely revolutionary. For the first time since life began, a species was developing the ability to impose its will on the environment, rather than simply adapting to whatever conditions it encountered. Instead of evolving thicker fur to deal with cold, these creatures could build shelters and make clothing. Instead of developing specialized digestive systems to process particular foods, they could use tools and fire to make almost any organic material edible. The implications of this technological approach to survival were staggering. Traditional evolution operated on time scales of thousands or millions of years, as random mutations slowly accumulated and spread through populations. But technological innovation could happen within a single generation, allowing these early humans to adapt to new environments and challenges at unprecedented speeds. As these capabilities developed and spread, human ancestors began having increasingly dramatic impacts on the ecosystems around them. The controlled use of fire allowed them to clear forests and create grasslands that were more suitable for hunting. Sophisticated hunting techniques enabled them to drive large mammals to extinction across multiple continents. And agricultural innovations eventually allowed them to reshape entire landscapes to support much larger populations than natural ecosystems could sustain. But the real transformation began roughly 10,000 years ago, when human societies discovered how to harness energy sources beyond their own muscles and the wood they could gather. The domestication of animals provided mechanical power for agriculture and transportation. The development of metallurgy allowed the creation of tools and weapons that were far more effective than anything made from stone or wood. And the establishment of permanent settlements created the social conditions necessary for increasingly sophisticated technological development. Each of these innovations accelerated the pace of human impact on natural systems. Agricultural societies could support populations that were orders of magnitude larger than hunter-gatherer groups, but they also required the conversion of natural habitats into farmland on an unprecedented scale. Metal tools and weapons allowed humans to modify landscapes and exploit resources that had previously been inaccessible, and permanent settlements created waste streams and resource demands that began to strain local ecosystems. The pattern that emerged during this period was fundamentally different from anything that had happened during previous mass extinctions. Instead of a single catastrophic event that eliminated dominant species and cleared the way for new evolutionary experiments, human activities were creating a slow-motion catastrophe that was gradually degrading ecosystems and eliminating species across the entire planet. The rate of this human-driven extinction accelerated dramatically with the Industrial Revolution roughly 300 years ago. The discovery of fossil fuels provided access to energy sources that were orders of magnitude more powerful than anything humans had used before. Steam engines, factories, and mechanized transportation systems allowed human societies to exploit natural resources and modify environments on scales that approached those of geological processes. The burning of coal, oil, and natural gas began pumping enormous quantities of carbon dioxide into the atmosphere, triggering climate changes that rivaled those caused by massive volcanic eruptions during previous mass extinctions. Industrial agriculture and urbanization converted natural habitats into human-dominated landscapes at rates that exceeded the ability of most species to adapt or relocate. And global transportation networks began moving species around the planet in ways that disrupted ecosystems that had been isolated for millions of years. But perhaps most significantly, human activities began operating on time scales that were completely unprecedented in the history of life. While previous mass extinctions had unfolded over thousands or millions of years, human impacts were causing environmental changes within decades or even years. Species that might have been able to adapt to gradual climate changes over geological time found themselves facing temperature and precipitation shifts that occurred faster than their generation times allowed for evolutionary responses. The result has been an acceleration in extinction rates that now exceeds the background rate by factors of hundreds or thousands. Conservative estimates suggest that species are disappearing at rates that are comparable to those seen during the most severe mass extinctions in Earth's history. More alarming estimates indicate that we may already be in the early stages of a biological catastrophe that could rival or exceed the great dying of the Permian period. What makes this potential sixth extinction particularly troubling is that it's being driven by a species that has the cognitive ability to understand what it's doing and the technological capability to change course if it chooses to do so. Unlike the cosmic and geological forces that triggered previous mass extinctions, human activities are theoretically under human control. The question is whether our species possesses the wisdom and collective will necessary to prevent a catastrophe of our own making. The parallels between current environmental trends and previous mass extinctions are both illuminating and terrifying. Like the volcanic eruptions that triggered the Permian extinction, human activities are rapidly altering atmospheric chemistry in ways that are making large areas of the planet uninhabitable for many species. Like the asteroid impact that ended the age of dinosaurs, human-driven habitat destruction is eliminating the environmental conditions that countless species depend on for survival. But there are also crucial differences that offer both hope and additional cause for concern. The global nature of human civilization means that our species has access to information about environmental changes as they occur, allowing for potentially rapid responses to emerging problems. Our technological capabilities provide tools for monitoring, modeling, and potentially mitigating environmental impacts that far exceed anything available to previous life forms. At the same time, the complexity and interconnectedness of modern human society creates vulnerabilities that could amplify the effects of environmental changes in unpredictable ways. Global supply chains, urban populations, and technological infrastructure all depend on stable environmental conditions and continued access to natural resources. Disruptions to these systems could trigger cascading failures that affect billions of people and accelerate environmental degradation. The species that are most likely to survive a human-driven mass extinction are probably those that possess characteristics similar to the survivors of previous catastrophes: small size, rapid reproduction, dietary flexibility, and tolerance for disturbed environments. Many of these species are already thriving in human-dominated landscapes, from urban-adapted birds and mammals to weedy plants that colonize disturbed soils. But the species that are most vulnerable are those that require large territories, have specialized habitat requirements, or reproduce slowly. These include many of the large mammals, birds of prey, marine predators, and old-growth forest species that capture our imagination and play crucial roles in ecosystem functioning. The loss of these species would not only impoverish the natural world, but could also destabilize ecosystems in ways that ultimately affect human welfare. The question of whether we're currently experiencing a sixth mass extinction is still being debated by scientists. But the evidence is becoming increasingly compelling. Current extinction rates, while difficult to measure precisely, appear to be far above background levels and are accelerating in many regions. Climate change, habitat destruction, pollution, and invasive species are creating multiple simultaneous stresses on ecosystems worldwide. Perhaps most ominously, many of the environmental changes being triggered by human activities are creating positive feedback loops that could accelerate the pace of change beyond our ability to control or adapt. Melting ice caps reduce the planet's ability to reflect sunlight, accelerating warming. Deforestation reduces the land's capacity to absorb carbon dioxide, increasing atmospheric concentrations. Ocean acidification impairs the ability of marine organisms to build shells and skeletons, potentially triggering marine ecosystem collapses. Yet the history of previous mass extinctions also provides reasons for cautious optimism about the long-term future of life on Earth. Every previous catastrophe, no matter how severe, was eventually followed by evolutionary recovery and the emergence of new forms of life that were often more complex and diverse than what came before. Life has proven to be remarkably resilient and creative in the face of even the most extreme challenges. The key insight from studying mass extinctions is that survival depends not on size, dominance, or apparent success under normal conditions, but on adaptability, flexibility, and the ability to exploit new opportunities as they arise. The species that inherit the Earth after major catastrophes are often those that seemed least important during the preceding period of stability. This suggests that even if human activities do trigger a sixth mass extinction, life itself will almost certainly survive and eventually recover. The question is not whether life will persist, but what forms it will take and how long the recovery process will require. Previous recoveries have taken anywhere from hundreds of thousands to tens of millions of years, timescales that are largely irrelevant to human concerns but crucial for understanding the long-term trajectory of life on our planet. For our own species, the lessons from deep time are both humbling and instructive. We are the first life form in Earth's history to develop the ability to study and understand mass extinctions, giving us unprecedented insight into the processes that have shaped the biosphere. We are also the first species capable of causing a mass extinction through our own activities, making us responsible for choices that could determine the fate of millions of other species. The cosmic perspective provided by studying ancient catastrophes reminds us that we are part of a larger story that extends far beyond human history or even human existence. The Earth has survived asteroid impacts, massive volcanic eruptions, and dramatic climate changes that make our current environmental challenges seem modest by comparison. Yet it has also shown us that the dominant species of one era can vanish completely, leaving only fossil traces of their former glory. As we stand at this crossroads in Earth's history, we have the opportunity to choose whether we become the agents of the sixth mass extinction or the first species to prevent one through conscious action and technological innovation. The choice we make will determine not only the fate of countless other species, but also the kind of planet we leave for future generations of all life forms. The story of the 5 great mass extinctions is ultimately a story about resilience, adaptation, and the creative power of evolution to find new solutions to environmental challenges. As we face the possibility of triggering a sixth extinction, we would do well to remember that life always finds a way to persist and flourish, even in the aftermath of the most catastrophic events our planet has ever experienced. The question is whether we will be part of that continuing story, or merely another chapter in the long history of species that failed to adapt to changing conditions. The evidence for this sixth extinction is mounting with each passing year, and the numbers are staggering in ways that should make us all pause and reflect. Scientists estimate that we're currently losing species at a rate that's between 100 and 1,000 times faster than the natural background extinction rate that has persisted for millions of years. To put this in perspective, imagine if time itself suddenly started moving 1,000 times faster, compressing centuries into days and millennia into years. But what makes this potential extinction fundamentally different from everything we've explored isn't just the speed at which it's happening. It's the fact that for the first time in Earth's 4 billion year history, the driving force behind a mass extinction is capable of understanding what it's doing and potentially changing course. We are simultaneously the asteroid, the volcano, and the only species that can study and comprehend the consequences of our actions. Consider the parallels between our current situation and those ancient catastrophes we've journeyed through together. The gamma ray burst that triggered the Ordovician extinction destroyed the ozone layer and flooded Earth with deadly radiation. Today, industrial chemicals have created a hole in the ozone layer, while our activities pump greenhouse gases into the atmosphere at rates that rival the most catastrophic volcanic eruptions in Earth's history. The massive volcanic eruptions that caused the Permian extinction poisoned the oceans and triggered runaway climate change. Today, we're witnessing ocean acidification from carbon dioxide absorption, rising sea levels from melting ice caps, and temperature increases that are pushing ecosystems beyond their ability to adapt. The scale of change we're creating rivals that of the Siberian traps, but compressed into mere decades instead of hundreds of thousands of years. The asteroid that ended the age of dinosaurs created a global impact winter that collapsed food webs from the bottom up. Today, we're witnessing the collapse of pollinator populations, the destruction of coral reef ecosystems, and the loss of primary forests at rates that are eliminating the foundation species that countless other organisms depend on for survival. Yet, there's something profoundly different about our role in this unfolding drama. The cosmic forces and geological processes that triggered previous extinctions were completely indifferent to the life they destroyed. A supernova doesn't care about the trilobites it eliminates. A volcanic eruption has no concern for the ecosystems it devastates. An asteroid follows the laws of physics without regard for the creatures it will impact. But we are different. We can study the fossil record and understand what happened during previous mass extinctions. We can model climate systems and predict the consequences of our actions. We can observe species disappearing in real time and comprehend the connections between our activities and their decline. Most remarkably, we can choose to change our behavior based on this understanding. This awareness brings with it a responsibility that no previous life form has ever faced. Every other species in Earth's history has simply followed its evolutionary programming, exploiting available resources and reproducing as successfully as possible, without regard for long-term consequences. They couldn't do otherwise because they lacked the cognitive capacity to understand the broader implications of their actions. We, however, have crossed a threshold that separates us from every other form of life that has ever existed. We can think beyond our immediate needs and consider the welfare of other species, future generations, and the planetary systems that sustain all life. The question is whether we will use this unprecedented ability to prevent catastrophe or become the first species to knowingly drive itself and countless others to extinction. The early warning signs are everywhere, and they're remarkably similar to the patterns we've seen in the fossil record. Ecosystems that took millions of years to develop are being simplified and degraded within human lifespans. Species that survived ice ages, volcanic eruptions, and dramatic climate changes are disappearing because they can't adapt fast enough to human-induced environmental shifts. In the oceans, we're witnessing changes that mirror the marine catastrophes of previous mass extinctions. Coral reefs, those underwater cities that support roughly 25% of all marine species, are experiencing bleaching events that are becoming more frequent and severe with each passing year. Ocean temperatures are rising, acidity levels are increasing, and oxygen-depleted dead zones are expanding in ways that echo the marine disasters of the Permian extinction. The massive schools of fish that once filled the seas are being depleted by industrial fishing practices that remove biomass faster than populations can recover. Marine food webs that evolved over millions of years are being disrupted from multiple directions simultaneously, creating conditions that many species simply cannot survive. On land, the situation is equally alarming. Tropical rainforests, those incredible reservoirs of biodiversity that took tens of millions of years to develop, are being cleared at rates that eliminate an area equivalent to several football fields every minute. These forests don't just harbor countless species. They also regulate local and regional climate patterns, store enormous amounts of carbon, and provide services that human societies depend on for survival. The grasslands and prairies that once covered vast areas of the continents have been converted to agriculture or urban development to such an extent that only tiny fragments remain. These ecosystems supported massive migrations of herbivores and the predators that followed them, creating some of the most spectacular wildlife displays in Earth's history. Today, most of these animals exist only in scattered populations that are too small and isolated to maintain their ecological functions. Even more troubling is the rate at which we're eliminating the large animals that play crucial roles in maintaining ecosystem stability. Throughout Earth's history, large herbivores and predators have shaped vegetation patterns, influenced nutrient cycling, and maintained the balance between different species. The ongoing defaunation, as scientists call it, is removing these keystone species faster than ecosystems can adjust to their absence. The parallels with previous mass extinctions become even more striking when we consider the speed at which these changes are occurring. The volcanic eruptions that triggered the Permian extinction unfolded over hundreds of thousands of years, giving some species time to migrate or adapt to changing conditions. The climate changes we're creating are happening so rapidly that many species are experiencing environmental shifts that exceed their ability to respond within their generation times. This temporal compression is perhaps the most alarming aspect of our current situation. Evolution operates on timescales that are measured in thousands or millions of years. But human-induced environmental changes are occurring within decades. It's like trying to outrun a bullet when you're adapted for marathon running rather than sprinting. Yet, even as we catalog these disturbing parallels, the lessons from deep time also reveal reasons for hope and strategies for action. Every previous mass extinction, no matter how severe, was followed by evolutionary recovery and the emergence of new forms of life. The survivors weren't necessarily the largest or most dominant species, but rather those that possessed certain key characteristics that allowed them to persist through catastrophic conditions. Small body size has consistently been an advantage during mass extinctions because smaller animals require fewer resources and can survive on limited food supplies. Dietary flexibility has also been crucial, as species that can exploit multiple food sources are more likely to find something edible when primary food webs collapse. Rapid reproduction allows populations to recover quickly once conditions improve, while behavioral adaptability helps species adjust to new environmental challenges. Perhaps most importantly, previous extinctions have shown that species with broad geographic distributions are more likely to survive catastrophic events than those with restricted ranges. This suggests that conservation efforts focused on maintaining connectivity between habitat fragments and preserving corridors for species movement could be crucial for helping biodiversity persist through the current crisis. The fossil record also revealed that mass extinctions, despite their devastating short-term effects, often accelerate evolutionary innovation in the long run. The elimination of dominant groups creates opportunities for surviving species to diversify and explore new ecological niches. The mammals that inherited the Earth from the dinosaurs that rose from the ashes of the Permian extinction, and the early vertebrates that survived cosmic catastrophes all represent examples of how life can seize opportunities created by global disasters. This pattern suggests that even if we are entering a sixth mass extinction, life itself will almost certainly survive and eventually recover. The question is not whether the biosphere will persist, but what form it will take and how long the recovery process will require. Previous recoveries have taken anywhere from hundreds of thousands to tens of millions of years, timescales that dwarf human history but are routine in the context of Earth's deep time. For our own species, the implications are both sobering and motivating. We have become a geological force comparable to volcanoes and asteroids, capable of reshaping the planet's surface and altering its atmospheric composition. But unlike those mindless forces of destruction, we possess something that could make all the difference: the ability to understand our impact and consciously choose to minimize it. The technologies that have enabled us to modify environments on a global scale could also provide the tools necessary to prevent or mitigate a mass extinction. We can monitor ecosystem health in real time using satellite imagery and sensor networks. We can model complex environmental interactions using supercomputers and artificial intelligence. We can engineer solutions to environmental problems using biotechnology and renewable energy systems. Most importantly, we can coordinate our actions on a global scale in ways that no previous life form has ever been capable of achieving. The same communication networks and transportation systems that have enabled our environmental impact could also facilitate the international cooperation necessary to address planetary scale challenges. The question is whether we will choose to use these capabilities to prevent catastrophe or continue on a path that leads inevitably to ecological collapse. The history of mass extinction shows us that dominant species can disappear completely, leaving only fossil traces of their former glory. But it also shows us that life is remarkably resilient and creative in finding solutions to even the most extreme challenges. As we stand at this crossroads in Earth's history, we have the opportunity to become something unprecedented. the first species to consciously prevent a mass extinction through coordinated global action. The choice we make will determine not only our own fate, but also the kind of planet we leave for the countless other species that share our world. The story of the 5 great mass extinctions reminds us that we are part of a much larger narrative that extends far beyond human history or even human existence. We are the latest chapter in an epic tale of survival, adaptation, and evolutionary creativity that has been unfolding for billions of years. The question is whether we will write ourselves out of this story or find a way to continue it in partnership with the other remarkable life forms that call Earth home. The lessons from deep time are clear. Life finds a way to persist and flourish even in the aftermath of the most catastrophic events our planet has ever experienced. The survivors are not necessarily the strongest or most dominant, but rather those that prove most adaptable to changing conditions. As we face the possibility of triggering a 6th mass extinction, we would do well to remember that our own survival may depend not on our ability to dominate nature, but on our wisdom to live within its limits and our creativity to find sustainable ways of sharing this remarkable planet with all its other inhabitants. The choice is ours, and the time to make it is now. The fossil record shows us what happens when planetary systems are pushed beyond their breaking points. But it also reveals the incredible resilience and adaptability of life itself. Whether we become agents of destruction or catalysts for a new chapter in Earth's evolutionary story depends entirely on the decisions we make in the coming decades. The Earth has survived asteroid impacts, massive volcanic eruptions, and dramatic climate changes that make our current challenges seem modest by comparison. It will undoubtedly survive whatever we do to it. The question is whether we will be part of its continuing story or merely another fossil layer marking the end of one evolutionary experiment and the beginning of the next. The remarkable thing about these ancient catastrophes is that they teach us something profound about the nature of change itself. When we look at the fossil record, we see that the most successful survivors weren't necessarily the creatures that seemed best adapted to stable conditions. Instead, they were the ones that possessed what we might call evolutionary flexibility, the ability to pivot when everything they thought they knew about their world suddenly became obsolete. Think about those small mammals scurrying through the post-asteroid wasteland 66 million years ago. They weren't impressive by the standards of their time. While massive dinosaurs dominated the landscape with their size and power, these little creatures were living quiet lives in burrows and tree hollows, eating whatever they could find and raising their young with care that seemed almost excessive compared to the reproductive strategies of their reptilian contemporaries. But when the cosmic hammer fell and the age of giants came to an abrupt end, those seemingly insignificant traits became the keys to inheriting the Earth. Small size meant lower resource requirements when food became scarce. Dietary flexibility meant survival when primary food sources collapsed. And that intensive parental care, which had seemed like evolutionary overkill, suddenly became crucial for raising offspring. In a world where environmental conditions could change dramatically within a single generation. The recovery from each mass extinction reveals patterns that are both predictable and surprising. Life doesn't simply bounce back to recreate what existed before. Instead, it explores entirely new possibilities that were impossible while the previous dominant groups occupied all the available ecological space. It's like a jazz musician improvising over a familiar chord progression, finding melodies that no one had ever imagined possible within that harmonic framework. After the Permian extinction eliminated over 90% of marine species, the few survivors didn't just rebuild the old ecosystems, they created something entirely new. The coral reefs that emerged in the Triassic were fundamentally different from their Paleozoic predecessors, built by different groups of organisms using different biochemical strategies. The marine reptiles that came to dominate the seas were unlike anything that had existed before, combining reptilian physiology with aquatic adaptations that produced creatures as different from their ancestors as whales are from wolves. This pattern of reinvention, rather than restoration, holds crucial lessons for understanding our current situation. If we are indeed in the early stages of a sixth mass extinction, the ecosystems that emerge on the other side won't be identical to what we're losing. They'll be something new, shaped by the survivors of our current crisis and the environmental conditions we're creating through our activities. The question isn't whether life will persist, because the fossil record makes it clear that life always finds a way to continue. The question is what forms that life will take, and whether our species will be part of the story that unfolds over the coming millions of years. The answer depends largely on how well we understand and apply the lessons that previous mass extinctions have taught us about the nature of survival and adaptation. One of the most striking patterns in the fossil record is how mass extinctions affect different types of organisms in predictable ways. Large-bodied species consistently fare worse than small ones because they require more resources and have longer generation times that prevent rapid adaptation to changing conditions. Specialists suffer more than generalists because their narrow ecological requirements make them vulnerable when specific habitat types disappear. And species with restricted geographic ranges are more likely to go extinct than those with broad distributions because local catastrophes can eliminate their entire populations. These patterns suggest specific strategies that could help both human societies and other species navigate the current crisis. For humans, this might mean developing more resilient and adaptable social and economic systems that can function under a wide range of environmental conditions. For conservation efforts, it suggests focusing on protecting species and ecosystems that have the characteristics associated with survival during mass extinctions. But perhaps the most important lesson from deep time is about the relationship between stability and change. The periods between mass extinctions, when ecosystems appear stable and predictable, are actually times when life becomes increasingly specialized and interdependent. Species evolve to exploit specific niches with remarkable efficiency, creating complex webs of interaction that can support incredible diversity, but also incredible vulnerability. The giant dinosaurs of the late Cretaceous represent the pinnacle of this kind of evolutionary refinement. They had evolved exquisite adaptations for their particular ways of life, from the enormous necks of sauropods that allowed them to browse vegetation over 100 feet above the ground to the sophisticated pack-hunting behaviors of predators like Velociraptor. But this very specialization made them vulnerable when environmental conditions changed faster than their long generation times allowed for evolutionary adjustment. In contrast, the small mammals that survived the asteroid impact were evolutionary generalists. They could eat many different types of food, live in various habitats, and adjust their behavior rapidly in response to changing conditions. Their lack of obvious specialization, which might have seemed like a disadvantage during stable times, became their greatest asset when stability disappeared. This dynamic between specialization and generalization plays out repeatedly in the fossil record and offers insights into how we might structure human societies to be more resilient in the face of environmental change. Economic systems that depend on narrow resource bases or specific environmental conditions are inherently more vulnerable than those that maintain diversity and flexibility. Social institutions that can adapt quickly to changing circumstances are more likely to persist than those that are rigidly structured around particular assumptions about how the world works. The speed of current environmental change also creates challenges that are unprecedented in the history of life. Previous mass extinctions, even the relatively rapid asteroid impact, unfolded over timescales that allowed at least some species to migrate to more suitable habitats or evolve adaptive responses. But human-driven changes are occurring so rapidly that traditional evolutionary responses may be insufficient for many species. This temporal compression means that survival in the current crisis may depend more on behavioral flexibility and physiological tolerance than on genetic adaptation. Species that can quickly learn new behaviors, exploit novel food sources, or tolerate broader ranges of environmental conditions may have significant advantages over those that rely primarily on genetically programmed responses to environmental challenges. The urban environments that humans have created across the planet represent a fascinating natural experiment in rapid adaptation to novel conditions. The species that thrive in cities, from pigeons and rats to various weedy plants, demonstrate the kinds of traits that may be crucial for survival in human-dominated landscapes. They're typically small, behaviorally flexible, tolerant of disturbance, and capable of exploiting resources that didn't exist in their ancestral environments. These urban adapters offer clues about what the ecosystems of the future might look like if current trends continue. Rather than the pristine wilderness areas that capture our imagination, the dominant ecosystems of the Anthropocene may be hybrid landscapes where wild species have learned to coexist with human infrastructure and activities. These won't necessarily be impoverished environments. They could be remarkably diverse and productive, just organized around different principles than the ecosystems we're familiar with. The fossil record shows us that mass extinctions don't just eliminate species, they also create opportunities for evolutionary innovations that might never have emerged under stable conditions. The mammals that inherited the Earth from the dinosaurs didn't just grow larger to fill vacant ecological niches. They developed entirely new capabilities, from echolocation in bats to sophisticated social behaviors in primates, that represented genuine evolutionary breakthroughs. Similarly, the current environmental crisis may be creating selection pressures that favor entirely new types of adaptations. Species that can tolerate higher temperatures, more acidic oceans, or fragmented habitats may evolve capabilities that are unprecedented in their lineages. The rapid pace of environmental change might even accelerate evolution in some groups, as strong selection pressures weed out individuals that can't cope with new conditions. For humans, this period of environmental upheaval could also drive innovations that fundamentally change our relationship with the natural world. The same technological capabilities that have enabled our environmental impact could be redirected toward developing sustainable ways of meeting human needs while maintaining ecosystem health. Advances in renewable energy, biotechnology, and artificial intelligence could provide tools for managing planetary resources in ways that support both human welfare and biodiversity. The challenge is developing and implementing these solutions rapidly enough to prevent irreversible damage to the Earth's life support systems. Unlike previous life forms, we have the cognitive ability to anticipate future consequences and the technological power to implement global-scale solutions. But we also have the same evolutionary psychology that drove our ancestors to exploit available resources without regard for long-term sustainability. This tension between our advanced cognitive abilities and our ancient behavioral programming represents one of the great challenges of the current era. We can understand the consequences of our actions and design solutions to environmental problems, but we often struggle to implement those solutions when they conflict with short-term interests or deeply ingrained behavioral patterns. The fossil record suggests that this kind of tension between capability and behavior may be inherent in the evolution of intelligent species. The same traits that allow for technological advancement, such as curiosity, creativity, and the drive to exploit resources efficiently, can also lead to environmental overexploitation, if not balanced by wisdom and restraint. Perhaps the most hopeful lesson from the history of mass extinctions is that life consistently proves more creative and resilient than we might expect. Even the most devastating catastrophes in Earth's history have been followed by evolutionary radiations that produced new forms of life more diverse and complex than what existed before. The Cambrian explosion that followed the late Precambrian extinctions, the mammalian radiation after the dinosaur extinction, and the recovery of marine ecosystems after each oceanic crisis all demonstrate life's remarkable ability to not just survive, but flourish in the aftermath of catastrophe. This doesn't mean that mass extinctions are good things or that we should be complacent about the current crisis. The suffering and loss associated with these events is real and tragic, both for individual organisms and for the ecosystems they're part of. But it does suggest that even if we fail to prevent significant environmental damage, life itself will continue and eventually recover in ways that we can't fully predict or imagine. The species that emerge from the current crisis, whether human or non-human, may possess capabilities and live in ecosystems that are as different from today's world as our current biosphere is from the Permian or Ordovician. They may find solutions to environmental challenges that we haven't considered, develop relationships with their surroundings that we can't envision, and create forms of complexity and beauty that we can't imagine. In the end, the story of mass extinctions is really a story about the power of life to persist, adapt, and create new possibilities even under the most challenging conditions imaginable. It's a story that reminds us that we are part of something much larger and more enduring than our individual lives or even our species' existence. We are participants in an ongoing evolutionary experiment that has been running for billions of years and shows no signs of ending. Whether we become a footnote in that story or a major chapter depends on the choices we make in the coming decades. The lessons from deep time suggest that survival depends not on dominance or control, but on adaptability, cooperation, and the wisdom to live within the limits of our planetary home. The Earth has survived cosmic catastrophes and geological upheavals that dwarf our current challenges. The question is whether we will learn from its history and find our place within its continuing story, or whether we will become another cautionary tale about the consequences of pushing natural systems beyond their breaking points. The choice is ours, and the time to make it is now. The fossil record shows us both the terrible consequences of environmental catastrophe and the remarkable resilience of life itself. As we stand at this crossroads in Earth's history, we have the opportunity to choose which path we will follow. We can continue down the road that leads to ecological collapse, or we can use our unprecedented understanding of natural systems to chart a course toward a more sustainable and hopeful future. The story of the 5 great mass extinctions teaches us that change is inevitable, but the direction of that change is not predetermined. Life always finds a way to continue, but the forms it takes depend on the conditions it faces and the opportunities it encounters. We have the power to influence those conditions and create those opportunities, not just for our own species, but for all the remarkable forms of life that share our planet. This is perhaps the greatest responsibility and the greatest opportunity in the history of life on Earth. For the first time, a species has the knowledge and capability to consciously guide the direction of evolution and the development of ecosystems on a planetary scale. How we use that power will determine not only our own fate, but the fate of countless other species and the future trajectory of life itself. The ancient catastrophes we've explored together remind us that we are part of a story much larger than ourselves, a story that began billions of years ago and will continue long after we're gone. Our role in that story is still being written, and the choices we make today will determine whether future chapters describe us as wise stewards of our planetary inheritance, or as another species that failed to adapt to the consequences of its own success. The Earth has shown us repeatedly that life finds a way to persist and flourish even in the aftermath of the most devastating catastrophes. The question now is whether we will be part of that continuing story of resilience and renewal, or whether we will become another layer in the fossil record, marking the end of one evolutionary experiment and the beginning of the next. The remarkable thing about this moment in Earth's history is that we're not just passive observers of these unfolding changes. We're active participants with the unprecedented ability to study our own impact and make conscious decisions about the future we're creating. Every previous mass extinction was driven by forces completely beyond the control of life itself, but this potential sixth extinction is being authored by a species that can read its own story as it's being written. Think about the incredible privilege and responsibility that represents. We can examine rocks that are hundreds of millions of years old and decode the chemical signatures left by ancient volcanic eruptions. We can study ice cores that preserve atmospheric conditions from thousands of years ago. We can track the movements of animals across entire continents using satellite technology and analyze the genetic relationships between species that separated millions of years ago. This wealth of knowledge gives us something that no previous life form has ever possessed: the ability to learn from the mistakes of the past and make informed choices about our future. We can see the warning signs of ecosystem collapse in real time and understand their implications. We can model the long-term consequences of our actions and adjust our behavior accordingly. Most importantly, we can coordinate our responses on a global scale in ways that could prevent catastrophe rather than simply react to it. The question that haunts me, and should haunt all of us, is whether we'll use this extraordinary capability to write a different ending to this story. The patterns we've discovered in deep time show us that mass extinctions aren't just random catastrophes. They're systemic breakdowns that occur when planetary systems are pushed beyond their ability to maintain stability. The early warning signs are remarkably consistent across different extinction events, and many of those same signs are flashing red in our current world. But here's what gives me hope. The same intelligence and technological power that has enabled us to alter planetary systems could also provide the tools necessary to restore balance and prevent collapse. We're already seeing glimpses of what this might look like. Renewable energy technologies are becoming cheaper and more efficient than fossil fuels in many markets. Conservation efforts are successfully bringing species back from the brink of extinction. International cooperation on environmental issues, while still imperfect, is creating frameworks for addressing planetary-scale challenges. The speed at which these solutions are developing gives me reason to believe that we might be approaching a tipping point where positive changes could accelerate just as rapidly as the negative trends we've been experiencing. The same exponential growth patterns that have driven environmental degradation could also drive environmental restoration if we make the right choices and invest in the right technologies. What the fossil record teaches us is that survival during times of rapid change depends on adaptability, cooperation, and the ability to find new ways of living when old strategies no longer work. These are precisely the capabilities that human societies possess in abundance if we choose to use them wisely. We've already demonstrated our ability to rapidly change our behavior when faced with existential threats. The question is whether we'll recognize the current environmental crisis as the existential threat it truly represents. The survivors of previous mass extinctions weren't necessarily the most impressive or dominant species of their time. They were the ones that proved most capable of adapting to new conditions and exploiting unexpected opportunities. As we face our own period of planetary upheaval, these same qualities of flexibility, resilience, and creative problem-solving may determine not just which species survive, but which ones thrive in the world we're creating. The story of Earth's 5 great mass extinctions is ultimately a story about the power of life to persist, evolve, and create new forms of beauty and complexity, even in the aftermath of unimaginable catastrophe. It's a story that reminds us that we are part of something much larger and more enduring than our individual lives or even our species' existence. We are the latest chapter in an epic tale of survival and adaptation that has been unfolding for billions of years. Whether we become a cautionary tale about the dangers of unchecked growth and environmental destruction, or a success story about intelligence and cooperation triumphing over short-term thinking and narrow self-interest, depends entirely on the choices we make right now. The fossil record shows us that dominant species can disappear completely, but it also shows us that life always finds a way to continue. The question isn't whether life will survive our impact on the planet. The question is what form that life will take, and whether we'll be part of the story that unfolds over the coming millions of years. The answer lies in our hands, and the time to write it is now. As we conclude this journey through deep time, remember that you are witnessing history in the making. Future paleontologists, whether human or some other intelligent species, will study this period in Earth's history and try to understand how the dominant life forms of the early 21st century responded to the greatest challenge they had ever faced. The fossil record they leave behind will tell the story of our choices and their consequences. Will they find evidence of a species that learned from the mistakes of the past and found a way to live sustainably on their planetary home? Or will they discover another layer of extinction marking the end of one evolutionary experiment and the beginning of the next? The story is still being written, and every one of us has the opportunity to influence how it ends. The Earth has survived cosmic bombardments, massive volcanic eruptions, and climate changes that would make our current challenges seem modest by comparison. It will undoubtedly survive whatever we do to it. The question is whether we will be part of its continuing story or merely another fossil layer, marking a moment when intelligence wasn't quite enough to overcome the ancient drives that brought us to this crossroads. The choice is ours, and the future is watching.